Good morning, everyone, and thank you for joining me today. I'm Dr. S.K. Singh, and I'm pleased to present to you on the topic of qualification of cuvettes used for UV visible spectrophotometry. In this session, we'll explore the key factors that influence the selection and proper use of cuvettes in spectrophotometry. We'll cover the types of cuvettes, their material properties, and how they impact measurement accuracy. I look forward to sharing this information with you and engaging in a fruitful discussion. Let's get started. Welcome to our introduction. In this section, I'll give you an overview of what we'll be discussing today. We'll start by establishing the key points that are essential to understanding the topic. I want to make sure we're all on the same page, so I'll explain these concepts thoroughly, but in a conversational way. This approach helps to highlight the most important ideas and makes the information more relatable. As we go along, I'll connect these points to the overall theme of the presentation, showing how each piece fits into the bigger picture. My goal is to set a clear foundation so that when we move into the more detailed sections, everything will make sense and feel cohesive. Let's take a closer look at the role of the cuvette in UV-vis spectroscopy. Essentially, the cuvette is where we hold our sample, and it needs to do so in a precise optical geometry. This means the way the sample interacts with light depends heavily on the cuvette's shape and size. Ensuring accurate transmission of UV and visible light through the sample is crucial, because any distortions here can affect our measurements. The cuvette directly influences how we determine absorbance, which is the core of what we're measuring. If the cuvette isn't perfect, or if it has even minor defects, it can significantly change the absorbance values we record. That's why parameters like accuracy, precision, linearity, and sensitivity are all impacted by the quality of the cuvette. Even small scratches, contamination, or variations in the path length, the distance the light travels through the sample, can lead to inaccuracies. So, when we're working with UV-vis spectroscopy, paying close attention to the cuvette's condition is vital for obtaining reliable and reproducible results. It all ties back to our overall goal of precise and accurate spectroscopic analysis. So let's talk about what cuvette qualification really means. Essentially, qualification is a documented process that confirms that our cuvettes meet specific optical standards, ensuring accurate measurements. It's also about verifying that the cuvettes are free from any defects that could impact absorbance readings. Plus, we need to make sure they comply with the requirements of the instrument and the method we're using. The main goal here is to eliminate any variability that might come from differences in cuvette quality, so our results are reliable and consistent. When we look at the applicable norms and guidelines, several standards come into play. For example, ICH Q2 R1 covers the validation of analytical procedures, including aspects related to cuvette performance. The USB provides guidelines on spectrophotometer performance and accessories, which include our cuvettes. Then there's 21 CFR Part 211, which addresses instrumentation and controls, ensuring quality in pharmaceutical manufacturing. And finally, the PH, your, sets specific UV-vis requirements. All these standards help us maintain rigorous quality control and ensure our measurements are trustworthy. Now, let's take a closer look at the qualification stages. These stages are closely aligned with instrument qualification, starting with IQ, which stands for Installation Qualification. This is the phase where we verify that the equipment has been installed correctly and according to specifications. Next, we have OQ, or Operational Qualification. During this stage, we test the equipment to ensure it's functioning properly within its intended operational parameters. Following that is PQ, or Performance Qualification, where we assess whether the equipment consistently performs as expected under real-world conditions. Focusing on the cuvette, the key point here is that the OQ and PQ tests are especially critical. Because the cuvette is a core component, verifying its performance during these tests ensures reliable and accurate results in your processes. Now, regarding cuvette specifications, there are typical specs that you need to verify. These include parameters like dimensions, optical clarity, and material integrity. Ensuring these specs are within acceptable ranges is essential for maintaining the overall quality and accuracy of your measurements. In essence, thorough qualification and verification of Cuvette specs helps safeguard the integrity of your analytical results, supporting the overall quality of your process. Let's take a closer look at the %RSD calculation. First, we find the mean of our measurements, which in this case is the sum of the values 0.012, 0.014, 0.011, 0.013, 0.015, and 0.013 divided by 6. That gives us a mean of 0.013. Next, we calculate the standard deviation, which is approximately 0.00153. To find the %RSD, we divide the standard deviation by the mean and multiply by 100, resulting in about 11.8%. Since this exceeds our acceptance limit, it indicates a fail in this reproducibility test. Now, moving on to blank reproducibility. The idea here is to measure the absorbance of a blank, which is just the solvent, across 6 different cuvettes. Our acceptance criteria are straightforward. The average absorbance should be less than 0.02, and the %RSD should be 2% or less. In our qualification test example, these criteria help us ensure that our blank measurements are consistent and reliable, which is critical for validating the accuracy of our analytical method and maintaining overall quality in our testing process. Let's take a closer look at the path length verification calculation. This step is crucial because it helps us ensure that our optical path length measurements are accurate. Essentially, we're verifying that the distance our light travels aligns with our expectations based on the setup. By doing this, we can confirm that our system is properly calibrated and that our subsequent measurements will be reliable. Remember, the overall goal here is to maintain precision in our data, and verifying the path length is a key part of that process. So, this calculation isn't just a technical step, it's a foundational check that supports the integrity of the entire experiment. Let's talk about handling and maintenance. It's essential that qualification includes following standard operating procedures, or SOPs, for handling our equipment properly. This means paying close attention to cleaning, using only substances that don't leave a film or residue that could interfere with measurements. When storing equipment or samples, make sure they are kept in dust-free, desiccated cases to prevent contamination or moisture damage. Always inspect everything carefully before use to catch any issues early. And a simple but important point, try to avoid fingerprints, as they can affect the accuracy of readings. Improper handling can lead to absorbance artifacts, which can compromise our results, so proper handling is critical. Now, moving on to the linearity test. This is where we verify that our instrument responds proportionally across a range of concentrations. We do this using calibration curves with standard solutions. These curves are fundamental because they ensure our measurements are accurate and reliable. When we plot the data correctly, we confirm that our method is linear, which is vital for valid quantitative analysis. Connecting all these points, proper handling, and regular calibration really underpin the integrity of our entire analytical process. Let's take a closer look at common issues and troubleshooting strategies. When working through any system or process, it's normal to encounter some hiccups along the way. The key is to understand the most common problems and how to address them effectively. First, identify the issue clearly. Sometimes, the root cause isn't immediately obvious, so taking a systematic approach helps. Next, check the basics. Things like connections, settings, or updates. These often solve the problem quickly. If those don't work, consult the troubleshooting guides or logs, which can offer valuable clues. Remember, documenting each step you take can save time if you need to escalate the issue later. Overall, troubleshooting is about patience, methodical thinking, and leveraging available resources. These skills not only resolve issues faster, but also help reinforce the reliability of the entire system, tying back to our theme of efficient and resilient operations. Let's talk about documentation requirements. When recording data, it's essential to include the cuvette ID or batch number to ensure traceability. You also want to document the qualification test results, which verify that your equipment or process is performing as expected. Calibration curves should be recorded accurately, as they are critical for data validation. Any deviations from expected results, along with the corrective actions taken, must be thoroughly documented to maintain transparency. Finally, you need to record the acceptance decision, indicating whether the data meets the required standards. From a regulatory perspective, the key expectation is that these records are traceable and support data integrity, aligning with the ALCOA Plus principles. This means data should be attributable, legible, contemporaneous, original, accurate, complete, consistent, enduring, and available. Ensuring these documentation practices helps uphold the quality and compliance standards essential in our industry. Now, let's wrap up with the key takeaways from this presentation. First, cuvette qualification is absolutely crucial for obtaining reliable UV-Vis data. If the cuvettes aren't properly qualified, our measurements can be off, which impacts the integrity of our results. Second, it's essential to follow regulatory expectations, such as those outlined by ICH, USB, and CFR. These guidelines help ensure our methods are compliant and our data is trustworthy. Third, qualification involves several important steps like OQ and PQ testing, along with thorough calculations and detailed documentation. These steps help verify that everything is functioning correctly and consistently. And finally, by properly qualifying our cuvettes, we significantly enhance the accuracy, precision, and overall integrity of our analytical data. This all ties back to our goal of producing high-quality, reliable results in our laboratory practices. For further support, please don't hesitate to reach out. If you have any questions or need additional information, I'm here to help. You can contact us through the provided channels. Thank you so much for your time and attention today. I really appreciate your engagement and look forward to supporting you moving forward.